Okay, in the last podcast, we talked about low pass filters. They let pass the signal that had low frequency, and high pass filters that pass the signal that had a high frequency. So now today I want to talk about band pass filters. And so to jump to the final story, a band pass filter is something that passes only signals of some designated frequency based on the design of your circuit. Essentially, signals that have frequency lower than that frequency are zero, and signals that have frequency higher than that characteristic frequency are also zero, right? So we just pass a small subset of the frequencies. And so it turns out there are a lot of ways to do this, and one of them, of those ways, is to have a resistor in series with the inductor and capacitor in parallel. And so we can kind of look at this and say, hey, what's the basic idea? At a very high frequency, the impedance of the inductor will be very large. The impedance of the capacitor will be essentially zero, and so the net resistance or net impedance of the inductor and capacitor in parallel will be zero, so there will be very little output voltage at high frequency. At low frequencies, the impedance across the capacitor will be very large, the impedance across the inductor will be very small, and so the net impedance of the inductor and capacitor in series will be very small, and so we'll have very little output voltage. And so you can imagine an inductor, capacitor, and resistor value that somehow there's a frequency somewhere in between, high and low, where this actually has a significant impedance, and we get some fraction of the input, maybe all, maybe some fraction across the output. And so that's what we mean by a bandpass filter, and this is essentially, well, this is how your radios used to work. We could dial in whatever frequency we wanted, we could hear our radio station. So here's the gain. We can go through the same procedure we did before. The gain is just the out over the in. The out is going to be equal to the current times the impedance of the inductor and capacitor in parallel. The signal generator voltage will just be the current times the total impedance of the circuit. We can substitute the values for the inductor and capacitor in parallel and the impedance of the resistor, and we can simplify that relationship. Okay, so now we can find the gain. What's the gain? The magnitude of the gain. We can do that. We get this complicated form. We can make some simplifications. We can define omega LC equal to 1 over LC, and omega LR is equal to R over L. And we can substitute that in this equation. And again, you can see this is a dimensionless equation, dependent on the frequency, but we're going to take this value times the input voltage, and it'll tell us the output voltage. So let's see that the behavior is what we think. At high frequency, this omega squared will be large, this value will be large, the denominator will be large, and so the gain will be 0. At low frequency, this value will be 0 or small compared to 1, so that'll just be 1. But then we have this omega squared in the denominator, and that'll make this value very big, so that makes the overall denominator large, and so the gain will be 0. So that's exactly the characteristics that we were looking for. And if you plot this particular function, you get this value, assuming that omega LR is equal to 1. Okay. Well, we can go through the same procedure, find the phase, plot the phase versus the angle, get something like this. When we're at low frequencies, the signal's out of phase. When we're at high frequency, the signal's out of phase. And we're at sort of the characteristic frequency, we're in phase. And so what is that characteristic frequency? That characteristic frequency is omega LR, or omega LC. It just depends on what's the inductor value and what's the capacitor value. Okay, so that's a bandpass filter. So that sort of takes care of the 3 types of filters: low pass, high pass, and band pass. It allows you to sort of pick what are the frequencies that you want to look at. Let's do one other thing. So this is just a basic thing. So take a look at this graph. So let's say I have a square function, and I want to find, well, what's the derivative or what's the integral of that equation? So take a few seconds, and in your mind, figure out, well, what's the derivative of the square wave going to look like, and what's the integral of the square wave going to look like? So again, the derivative is really just going to be the change, and so when does the square wave change? Well, only when it makes a transition. And so if we take the derivative, we're really just going to get some kind of delta function, a negative delta function, a positive delta function, negative delta function, depending on the slope of the square wave. And if we thought about what's the integral is just the area under the curve. Where the area is positive, we're going to increase, the integral will be increasing, and where the area is negative, it will be decreasing, and so we may get something that looks like this. Okay, so now in our minds we say, oh, we have a square wave, we kind of know what the derivative looks like and the integral looks like. So let's look at one other thing. It turns out that if you differentiate and integrate with complex numbers, it amounts to multiplying by a constant. So let's see how that would work. So first, assume that the voltage is going to be, we can write as some oscillatory function in polar form. So this function oscillates, and that's the potential. And then we take the derivative. So the derivative of an exponential is just going to be j omega in this case. And so we just get the derivative of the potential, which is going to be j omega times the potential. Then we can do the same thing with the integral. We can do the integral of the potential with respect to time, put in our function, and it turns out that the integral is just 1 over j omega times our potential. So this is what I said before. So to differentiate and integrate when we're in these complex numbers, it amounts to multiplying or dividing by a constant, in this case j omega. Okay, so why is that important? Well, there's low pass and high pass filters can also be used as an integrator or a differentiator. So let's look at the differentiator. You look at the high pass filter. So this is where we have an input voltage, we have an inductor and capacitor in series, and we're going to take the potential or the output signal across the resistor. When we do that, if we look at very low frequencies, so this is not when we're getting a big signal, and that essentially means omega is much, much less than omega RC, or omega RC is much, much less than 1. Then we can look for the gain. The gain will approximately be 1. This is the gain from before. But if this number is very small, then this value is very large. We can ignore this 1, and this approximates the j omega RC. Now remember, the gain, the V out is just the gain times V in, and so we can approximate that if we're in this low frequency region. It's just going to be j omega RC times the input voltage, but we can separate that RC out, and then j omega times the input voltage, right? That's really just dV and dt, because differentiation is just multiplying by a constant, in this case the special constant, j omega. And so what's this look like? So down here I have the square function, and so if you put that square function into a high pass filter at low frequency, where low frequency is defined by the characteristic frequency of the circuit, then you'll output something that looks like this. You can do the same thing to find an integrator, only this time it's going to be a low pass filter at high frequency. Again, this is when your output signal is going to be very small, and this occurs when omega is much, much bigger than omega RC, or omega RC is much, much bigger than 1. And in that case, the gain will approximate to be 1 over j omega RC. And so, again, the output voltage is with the gain times the input voltage. The gain approximates to 1 over j omega RC. And so we can pull out the 1 over RC, that leaves 1 over RC times the input voltage divided by j omega. Well, that's just the input voltage divided by our special constant. That amounts to the integral of dN dt. And so that's approximates as an integrator to the output of the derivative of the input. So we have our input voltage square wave, and if you plot that, you'll get the following circuit, or the following output.